Good morning, everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this session, we'll be talking about American column curves. In the previous class, we discussed about several different types of column curves. We also discussed about the buckling research and code writing bodies. In the US, it is CRC, also known as Column Research Council, SSRC, Structural Stability Research Council, as well as AISC, the American Institute of Steel Construction. In the Europe, it is ECCS, European Convention for Constructional Steelwork. In the British, we have British Standard Institutions, and India, we have Bureau of Indian Standards. The corresponding curves of column are given as CRC as Column Research Council, Basic Column Curve, SSRC is SSRC Multiple Column Curves, and AISC is based on the CRC curve. ECCS is based on multiple column curves incorporated into most European national codes. The following were discussed in the previous classes. Now, in multiple column curves, as per Eurocode, we have the Perry-Robertson formula, sigma p by sigma y equal to 1 by p plus root of phi square minus lambda square, which is basically the reduction factor. P is given as 1 plus eta plus lambda square by 2. Lambda square is 1 by n equal to sigma e by sigma y. Eta is given as alpha into lambda minus 0.2. Phi is given as 0.5 into 1 plus alpha into lambda minus 0.2 plus lambda square. We also talked about the imperfection factors for various buckling curves. We also talked about various classes of buckling. This is similar to the column design curve used in IS 800. In IS 800 also, we have a similar reduction factor given as 1 by phi plus root of phi square minus lambda square. The imperfection factors are identical to the Eurocode given here. And we have the same set of curves A, B, C, D. The only difference is here we do not have A0 in IS 800, whereas there is an A0 curve in the Eurocode. So we have this Perry-Robertson formula, and using this Perry-Robertson formula, so now we need to select the buckling curve for the cross section. We have three steps. First, we have to identify the aspect ratio of the cross section, followed by the thickness, followed by the buckling direction, whether it is major axis buckling or minor axis buckling, which leads to the buckling class. So we have this curves that I mentioned, the reduction factor versus the non-dimensional slenderness ratios, which gives the 5 different classes of buckling curves. We also discussed the buckling classes in the previous section. More importantly, we discussed that there is a rational basis to it. We also discussed about how these curves are classified and what are the importance of each curve and what type of cross-section fabrication to be selected, the type of cross-section, whether it is annealed, whether it is welded, whether it is buckling about major axis, minor axis, is it singly symmetric, is it doubly symmetric? All these things were discussed in the previous class. So what is the takeaway here? The takeaway here is that the research carried out in Europe by Beer and Schultz, Jacquet and Fintesco led to the development of multiple column curves which were later adopted by ECCS. The values of imperfection factor alpha as well as the buckling classes were thus determined based on research conducted above on various columns. The imperfection factor changes with the buckling class of the column. The design strength curves provided in IS 800 2007 is derived from ECCS multiple column curve approach. In this lecture, we will discuss American column design curves. So the American column curve AISC is basically coming from the CRC curve, which is the Column Research Council recommended a formula in the form of a parabola. We have sigma critical is given as 1 minus half into KL by R divided by pi into root of E by sigma sub P the whole square into sigma Y for KL by R less than pi into root of E by sigma sub P. And the next one is pi square E divided by KL by R the whole square, which is for long columns for KL by R greater than or equal to pi into root of E by sigma sub P. So let's look at it. The value of sigma sub R, which is the residual stress, is taken as 0.5 into sigma Y, which is a compromise to cover both strong and weak axis buckling of hot rolled wide plank sections. So sigma R is equal to 0.5 into sigma sub Y, which implies sigma sub P equal to sigma Y minus sigma R, which is equal to 0.5 sigma Y. Here we have KL by R greater than or equal to pi into root of E by 0.5 sigma Y. Essentially, we are substituting 0.5 sigma Y for sigma sub P, and we can rearrange this as KL by R into 1 by pi into root of sigma Y by E, which is greater than or equal to root 2. We also know that n equal to sigma critical by sigma Y and lambda equal to KL by R into 1 by pi into root of sigma y by E. So this means that this equation that we have seen here at the bottom can be represented as lambda, which is greater than or equal to root 2. So when we express this entire equation above, which is in the form of sigma critical in terms of non-dimensionalized load, we have n equal to 1 minus lambda square by 4 for lambda less than root 2 and 1 by lambda square for lambda greater than or equal to root 2. When we plot n versus lambda, we have the CRC parabolic curve, which is shown in the pink color here, and the one that is in the dark blue is the Euler curve. So the cutoff point here is root 2. To the right of it is elastic and to the left of it is inelastic. Now, let us look at the safety factor adopted for AISC curve, and it is given as factor of safety equal to 5 by 3 plus 3 by 8 into KL by R divided by root of E divided by sigma P into pi minus 1 by 8 into KL by R divided by pi into root of E by sigma sub P the whole cube for KL by R less than pi into root of E by sigma sub P. And it is 23 by 12 for the long columns for KL by R greater than or equal to pi into root of E by sigma sub P. So we know that again n equal to sigma critical by sigma y, lambda equal to KL by R into 1 by pi into root of sigma y by sigma E. So this can be expressed in a non-dimensionalized form as n equal to 1 minus lambda square by 4 for lambda less than root 2 and 1 by lambda square for lambda greater than or equal to root 2. The corresponding factors of safety can also be expressed as 5 by 3 plus 3 by 8 into lambda by root 2 minus 1 by 8 into lambda by root 2 the whole cube for lambda less than root 2 and 23 by 12 for lambda greater than or equal to root 2. So we can compare it with the specification of structural steel buildings given by AISC. So the allowable stress is given as in the formula E21, and here let's look at a deeper look at the safety factor, which is at the denominator. We have 5 by 3 plus 3 into KL by R divided by 8 into C sub C minus KL by R the whole cube divided by 8 into C sub C the whole cube. So we have that KL by R divided by C sub C equal to KL by R divided by root of 2 pi square E divided by sigma Y, and which gives rise to the value KL by R into 1 by pi into root of sigma Y by E into 1 by root 2. So this gives rise to the equation KL by R divided by sigma sub C equal to lambda by root 2. So now on comparing with the specifications, we have the similar equations for the factor of safety for the inelastic column curve as well as for the elastic column curve. Now when we plot that in the same plot, we have this AISC curve here, which is much lower because it is including the factor of safety. However, research shows that the CRC column curve is not adequate for all the columns. There is a shift from single column curve to multiple column curves. The single column curve cannot cover the wide scatter band adequately, either too conservative or unsafe. So as you can see from the right hand side, close to 100 experiments were carried out for centrally loaded columns. The test results are plotted in a non-dimensionalized fashion. You can see the large scatter is there in the test results. So there cannot be a one single curve that can cater to a wide range of scatters. Research conducted between 1950s and 1970s have identified the different strength reducing factors, transforming a single scatter band into multiple scatter bands associated with identifiable classes of columns, hence calling for multiple column curves approach in column design. Now from single column curve to multiple column curves was based on a large number of computer models and numerical simulations of various groups. SSRC column curves were suggested. This is based on the research report carried out at Lehigh University. The research report is shown here by Behaude and al. in 1971. You can see a number of columns with various configurations have been tested. So Behaude assembled experimental column research curves of various types of shapes, steel grade, etc. And he got multiple column curves. You can see the number of column curves on the right hand side of this figure. So in order to make sense out of it, we need to classify the column curves on some kind of a logical approach. Behaude then observed that there were definite groupings among the curves, and from these, 3 subgroups were identified. So you can see that the group 1 contains a number of different types of cross-sections as well as different fabrication methodologies, and it is classified as group 1. The figure is shown on the left hand side. Then there is group 2, which is slightly lower load carrying capacity with the different types of cross-sections as well as fabrication methodologies, which comes under group 2. The third one is the group 3, which is much lower in strength, as you can see here, again for various types of configurations and fabrication methodologies. Based on the experimental as well as numerical simulations, 3 column curves were proposed by Behovde and Tall. Curve 1, as you can see here, is shown at the top. The middle one is curve 2, and the last one is curve 3. All these curves were based on an initial out of straightness of L over 1000. The multiple column curves proposed by Behovde and Tall were yielding similar results to ECCS multiple column curves. So you can see the multiple column curves from Behovde and Tall and the ECCS column curves both merged together on the right hand side of the figure. The one shown on the right hand side is basically the idealized multiple column curve shown in the red color arrow mark based on the work carried out by Behovde and Tall. And the one that is shown in the blue color basically is the dotted curve that is getting highlighted, is based on the proposed European convention column curves. Behovde's multiple column curve and ECCS multiple column curves were very much similar. Further, SSRC column curves were established based on the 3 equations proposed by Behovde and Tall. So SSRC curve 1 is given here, curve 2 as well as curve 3. You can see that each curve has 5 subdivisions. It is based on the slenderness lambda. So when we plot n versus lambda, we have the Euler curve as well as the SSRC curve 1 shown in red color, SSRC curve 2 which is shown in the violet color, and SSRC curve 3 which is shown in the cyan color. The current American Design Code AISC 360, however, does not consider multiple column curves. Why? The original reluctance to adopt multiple column curves for the American structural steel design specification was founded on the belief that the design criteria would become too complicated. Behovde and Birkmore 1979 and Behovde 1988 extended the column research to ensure that all conceivable column types and materials would be properly assigned to one of the 3 strength categories. It was observed that the largest group of data clustered around SSRC column category 2P, and thus it was decided to use only one column curve, which is the SSRC column category 2P for all column types. So SSRC column curve 2 was selected for the AISC 360 design specifications. So an exponential form is proposed as sigma critical equal to e power minus 0.419 lambda square, which again was simplified as sigma critical equal to 0.658 power lambda square. So the AISC 360 specification gives the following values: 0.658 lambda square into sigma y for lambda less than or equal to 1.5 and 0.877 by lambda square into sigma y for lambda greater than 1.5. Now, how did we get 0.877? At lambda equal to 1.5, we have sigma critical equal to 0.658 into 1.5 the whole square into sigma y, which gives us the value 0.3899 into sigma y. Now, this should be equal to 1 by 1.5 square into constant, which is what we are planning to determine, into sigma y. So, which gives rise to the value 0.877 by lambda square into sigma y. The 0.877 is the constant, and the lambda square at the bottom is basically at lambda equal to 1.5 is the value that we get. So we have this equation here. We know that sigma critical is 0.658 lambda square into sigma y for lambda less than or equal to 1.5, 0.877 by lambda square into sigma y for lambda greater than 1.5. Here we have sigma y by sigma e is equal to lambda square. When we compare it with the codal provisions here, the right side of the codal provisions is given here. From the screenshot, we can observe that it is very similar to the values that are derived from these equations, the top one as well as the bottom one. Here in the bottom one, we can see that it is given in terms of F sub E, which is sigma E, equation E 3.3 in the codal specifications. Now, how did we get that sigma E? Basically, we know that sigma y by sigma E is equal to lambda square. So, sigma y by lambda square is equal to sigma E. which means that sigma critical is equal to 0.877 by lambda square into sigma y. So which gives rise to the equation sigma critical equal to 0.877 sigma E. We should understand that sigma E equal to pi square E by KL by R the whole square, which is the elastic critical buckling stress. Substituting this value of sigma E ensures that sigma critical accounts for the limit state of flexural buckling alone. What about other types of buckling? We will see that in the coming classes. Thank you very much.